hit record so I can shut up now. Okay, so we're recording now, and this is for burn-in. Basically, we don't want to send those chips that break early to the customers because it upsets people when they power up their iPhone and 5 minutes later it's dead because the memory chip is gone. That really upsets. And then you have to throw away a whole iPhone and start over again, or get somebody to repair it. So this is just a voltage reference circuit, and this is a voltage pump circuit. Basically, it's through the miracle of charge pumps that you learn about in power electronics. But the idea is if I keep on pumping the voltage into this capacitor, the charge has to go somewhere, and it's going to get built up in this node B, and just slowly increase it until it's fully charged, and you will have a charge pump. This is a simple DVC2 generator. It's basically an inverter with its input tied to its output. Only stable state for an inverter with its input tied to its output is both of those equal VCC over 2. So that's one way to do it. It doesn't exactly equal VCC over 2, so that's why we put that little VCC over 2 connection on there to guarantee that it actually happens. Signal integrity is a big deal, and it's becoming a bigger deal as chips go faster and faster, and as our DDR numbers keep getting higher and higher. That output driver has to deal with a really tough environment. You don't know what the PCB designer is going to hook up to, so you've got to be ready for anything, including static discharge, bad RF mismatches, packaging parasitics, and of course really high speed signals. There's a lot of different signaling standards. A lot of this is kind of like narrowed down to a couple of standards, but they still change occasionally, so you've got to keep an eye on that. These eye diagrams, you see the big eye, that's a good sign. It means that both the input signal, there's not a lot of jitter in that, so it's not jumping around a lot. I'm getting consistent timing from transition to transition, and I'm getting the transitions occurring roughly at the same speed. Those are the kinds of things that give you a good eye diagram. Now, normally when we deal with things on our first order, we can think of transmission lines having delays, and they look like RC charging. And that is when you get something like that, an RC charging curve. If you get something that looks like this is due to ringing in the line. You have impedance mismatches. Ringing in the line means signals going forward, bouncing back into your input signal, and going back and forth like that. There's a lot of people who have studied this for a really long time. They're called RF engineers. If you get into a problem like this, you go find one and you talk to them, or you learn, and then you learn, and that will really help you out. I can't tell you what you're going to be doing for a living. If Zach gets a job at General Dynamics, he's going to know all about this stuff in about 2 years.
Actually asked me that question. But the answer was impedance matching.
Yeah. Oh, okay.
Yeah, it's a real thing.
It is a real thing. It's pretty much what you do as your first year as an RF engineer. Match impedances, yes. Go ahead, let's all run away.
Yeah,
I have uninstalled McAfee.
Difficult to fully uninstall it.
Yeah, okay. I have uninstalled it, but the pop-ups keep coming. Okay.
Because McAfee functions as malware.
McAfee is malware.
Yes, yes. It's the worst virus on my computer.
I remember when you essentially made you install their own type of malware. Yeah. It was like my freshman year. There was like a spyware they made you install to use the internet.
Wow.
Yeah, that's where nowadays it's called Zoom.
Yes. Everyone's watching all my Zoom channels. I really don't think people have enough time to do this, to listen to me. The output buffer, now you got to remember, from an RF designer's point of view, those pins all have inductance on them. Both on the output driver, oh great, it's doing this thing again. Let me do.
Not letting you run.
Oh, there you go. I figured it out. There's a magic button.
No, it's like-
Okay, so you have inductance on the pins, you have capacitance on the pins, you have a transmission line connecting the driver and the receiver. It has inductance on its pins. The power system for this has inductance, and hopefully this is going to a good ground plane, so it has less inductance. And then you have return paths. Your ground paths have inductance on there, and there's loops in there that could potentially oscillate. So you have to be careful with all those connections if you're a printed circuit board designer. Yeah, and I don't want to talk about the other thing. It's just, I don't have enough time for that. Latch up, the thing that we learned about latch up is there, if you look at this, you can make all kinds of NPN transistors if you put a P well, or if you put an N well in there. You can find these parasitic NPN transistors that do act like NPN transistors, and you can get this horrible structure that's like a SCR, silicon controlled rectifier, NP. It gets a pulse of current into its base. Basically, you cannot shut it off without putting a really high voltage across there. This will destroy your chip. The best way to get rid of this is not to put any PMOS transistors in your output driver, because that's where you can't control people putting pulses of currents on things. ESD is a big deal. There is ESD protection inside the pad for all of your connections to the outside world on any rationally designed chip. Needless to say, the Aladdin chip did not have any ESD protection on it because the astronomers hated that. They would lose a couple of electrons. This protects you from someone accidentally a tiny little spark from destroying your device. It adds a lot of reliability to your system. If you want to know more about signal integrity, we'll talk about it in 490 in the fall too. Big thing we've got here is when we have impedance mismatches. We've talked about this some in here too. If my source resistance doesn't equal the characteristic impedance of the line, you get signal bouncing back into your source, and you get this little ringing here that looks like an underdamped system. And it will slow down the maximum speed you can operate at. Now, the only way to get around this, oh no, we're not quite there yet. Every time your source impedance does not equal your load impedance, your Z0 of your line, you get reflection. And you should have learned about this in 364, these reflection coefficients with transmission lines. And this is a real thing, and it's like Zach, who just interviewed at General Dynamics. That was one of the first things they asked him about was impedance matching. At least he knew the word. Okay, that's the way I do this. So what this does here is this is a calibration circuit on the output pad of your pen, where your pins for the memory chip are going, or any other chip are going, that will actually measure the voltage that you're sending, and make sure you're getting the maximum power out. And you can tune the impedance of that pad on the fly to match whatever the printed circuit board designer chose to use as a characteristic impedance within a certain range. And most printed circuit board lines have like a certain range of characteristic impedances. It's not perfect. You can terminate. This is basically a way of matching. Usually the RF way of matching is to put inductors or capacitors here to make it look closer to Z0 through the magic of the Smith chart. I really don't want to talk about this. It's a bunch of standards. It's a bunch of standards. Then we went into semiconductor physics. If anybody's still there, or anybody's still listening, or if you just went and I don't know, made some coffee, turned on a movie, whatever's going on. Okay. Yes, so you were at least alive, or maybe you're a Zoom bot. Okay. So given the MOS physical structure, we want to find out what influences the threshold voltage and the leakage and all that good stuff. This is an amazing slide if you understand this. C equals epsilon A over D. I don't know how many times I've used that in my life, quite a few. And then people think you know what you're talking about. Yeah, never mind. Basically what we do with p-n junction diodes here, we have this charge accumulation at the junction, because on the p side, on the p side, the electrons are attracted and they get concentrated right on that side of the junction before they find a hole and recombine. So I get this charge distribution here. That's in the depletion region. If I integrate that through the magic of Poisson's equation or something like that, if I integrate that, I get a, whatchamacallit, I get an electric field. This is an electric field, just due to that charge concentration. If I integrate electric field, I get voltage, and I get the structure across here, and this is the built-in potential of the junction, and yes, it's measurable and it's real. I got into an argument with Colt about that recently. When I go across the MOS structure, so this is the part of the transistor where it's metal oxide semiconductor, it's just the MOS capacitor part of it. I have three materials hooked together. The convention is we make the Fermi levels line up, and you did the homework on that, and I'm running out of time, so I don't want to talk about physics. MOS structure, probably not a lot of this on the exam. We did the flat band voltage. The big thing we got here is the gamma, the body bias coefficient. This is the one that determines how much your leakage changes with body bias. You can tune that basically by using the magic of materials. That's the only thing that will get you there. You have to change the materials. There's a lot of research going into that. The threshold voltage, where did it come from? It is basically based on material properties. And this is the body bias part of it. We get there by changing the materials. We can change the doping and influence it, but not a whole lot else. Please, this is like doing a core dump of an entire semester.
Like I said, we're speed running.
We're speed reading 490.
Doing Flash so fast he's already disappeared.
Yes, I am the Flash. Memories, semiconductors, everything, it's a cyclical industry. You got to learn to hang on during the bad times and be happy and grab the cash during the good times, and save money so you can ride out those storms. 2001, I was okay. I was working on soft money, but I was at JPL. The soft money got a little tight. That was about it. 2008, I was homeschooling. The only person in my house got fired from Micron. No, not Micron. The horrible evil one, Microsoft.
Horrible evil one.
Horrible evil company. Got fired from Microsoft. We had to put our house on the market. All kinds of horrible things. But we had enough money in savings that we could write it out. Keep that in mind. You don't want to spend it all. Be careful. Most important life lesson you can have. Flash, we've got that floating gate in there. We have to find ways to force electrons in there. That involves a lot of energy. High voltages and high currents is basically the way you do it. It's fairly destructive. These cells burn out all the time. I've got like 5 minutes to finish this story. The way we read a NAND, okay, don't encourage me. The way we read a NAND flash is we turn on every transistor in the row, except for the one we want to read. And the one we want to read, we give it a 50-50 chance of turning on. If it's programmed for a 0, it will turn on, and if it's programmed for a 1, it won't. So we have to, it's a very high power consumption type of thing. A lot of capacitance to charge. We read out a block at a time. You cannot read out 1 bit from a NAND flash, but everybody wants large amounts of data. So limiting this to a whole bunch of bits, doesn't bother anybody. And then we talked about imagers, and yeah, he's like my brother. He's like my big brother. That was only a couple years older than me, not 10 years older than me. We're a lot alike. I miss me too. Sabrina was a really good person too. Okay. Yeah, I miss those guys. So the image sensor basically silicon sees, because it has the band gap is such that it will see anything above at a shorter wavelength than 1 micrometer, which is basically in the visible. At the higher, as you get past, it's almost like just right. Silicon was made for seeing visible light, because if you get into the UV, if you start getting into the UV, then the UV photons get absorbed by the silicon and they never make it through to the imager. So it's almost perfect for seeing invisible light. And we just talked about this. So I've got like 3 minutes.
This was yesterday.
This was yesterday. Let's not just do it again. And yes, I am going to miss some of you.
So, yeah, I love that line.
It's been fun. It's strange though, because I mean, it's just like I've gone through this so many times. It's like you're in 280, or worse yet, you're like in 188, and I just don't even want to talk to you because you're freshman, right? And when you go through this process, and you're just going to ask stupid questions, and you're going to be annoying and high maintenance, and then you get into 280, and I still don't like you when we're talking about linear systems. And then we get into MOSFETs and you start making some sense.
I think one of the only reasons you put up with me back in 280 was because you knew I was Yuan's friend.
Yes, that really helped. Yuan told me to keep an eye on him. And then you get into 280, get to the end of 280, and I actually start liking some of you. And then it's like 380, and it's like suddenly there's these people I can talk to about things nobody else wants to talk about. And you probably still don't want to talk about transistors, but you'll listen to me at least ramble on about transistors for hours on end, so I tolerate you guys. And then you get into 490, and it's just like, okay, I can do like this core dump on you and kind of like tell you how things actually work in the real world, and it's great. And then you graduate, and I never see you again.
I like talking about pretty much everything in 380 except for body plots.
Yeah, nobody like, well.
They asked me that question too.
Yes.
I didn't quite remember.
Okay, but you knew what they were.
They asked me what was Bodhi plot, and to describe it, that was the question.
Okay.
I don't know if I could answer that question.
Just say it's a frequency response curve, and they'll think you know what you're doing. Okay, that is that.
What he said, I couldn't recall it at the time.
Okay.
I do remember now.
It's a frequency response curve, and does.
And you could say that you've seen them before.
I have seen. Started talking about them going down by 60 dB per decade.
20 dB per decade, and
I can talk about how I had to borrow a mini USB cord from you so that I could download a Bodhi plot processor on my calculator.
a Bodhi plot processor on your calculator.
So that I could.
So you could draw them on a test without actually having to think about it?
Yes.
Oh, brilliant. That is a good engineering decision right there. Okay, let's see who is here that wasn't here before. Bryce, I got you. Myrna.
Well, I do accept that.
Benjamin, you're not here.
I mean, you understand the concept.
Yeah.
Nolan.
I'm sure they use calculators too. So.
No, they don't use calculators. They have a much better thing right here. They don't.
Calculators with keyboards.
Yeah, they have calculators with big keyboards.
No.
Yes, it does. I never had a calculator when I was working. If I was either sitting in front of my computer, or if I was in the lab, the very worst, it would be too long. The very worst thing that you could do is whip out a calculator. The very best thing you could do is be the first person to be able to calculate whatever numbers he was spitting out.
Yeah, well, ask me.
And it was usually either me or me too.
Ask me to find percentages and something I can do most of it.
Yeah. ballpark estimates, yeah.
Because percentages and decimals and things, because, when I was-
Okay, you guys can go. I've got roll over. You can stay and listen to us babble.
my dad bullied me a little bit on learning how to think percentages in my head.
Oh,
It is.
we would go to Saskatchewan every summer, 2,500 miles in the car with my dad. Four other kids in the car, right?
Live in Saskatchewan?
Yeah, I lived in Saskatchewan, but
I used to-
when we were in Atlanta, when we moved back to Atlanta, we
Thank
drive-
you, Julie.
Okay, I'll see you, Susan. We drive back and forth, and my dad would make things like convert kilometers to miles and Celsius to Fahrenheit and calculate square roots in my head. This was what he did for 2.5 days. How he kept driving. He would not make anybody else do that. I was the only one.
Yeah, my dad would have me do that for decimals and percentages, whenever he and I would drive down to Phoenix, take a load of scrap metal down,